Okay, so we've got these equations that apply to motion on any interval by starting from the assumption of uniform acceleration, because these equations only apply when acceleration is uniform, and they synthesize the whole thing. They follow from what we get when we start with A equals constant and define V naught to be V equals zero velocity, Vf to be the final velocity, and so forth. And then define, our Vi and our Vf and our Xi and our Xf to be the velocity and position, the velocities and positions at time t equals Ti and t equals Tf. We do all this, we get this. Where delta t is Ti minus Tf, delta x is Xi minus Xf. Sorry, delta t is Tf minus Ti, delta x is Xf minus Xi. So there it is. Okay, well, much easier. Derivation, we don't have to do all this algebra, we don't have to go all this trouble, we don't have to use any calculus. If acceleration is uniform, your v versus t graph is linear, which means that for any interval lasting delta t time, you have some initial velocity and some final velocity. So on a velocity versus time graph, you have this trapezoid. You have delta t, Vi, and Vf. Now, those are our original quantities, so just to emphasize it here. We'll write over those in yellow to indicate that these are the quantities that we start with. And then in terms of these three quantities, we can calculate the slope and we can calculate the area, because once you know the two altitudes and the width of a trapezoid, it's very easy to get the slope and the area. Okay, well, the slope is rise divided by run. The rise is Vf minus Vi, the run is delta t, so there's your slope. Now, if we interpret the slope, what is the slope of a v versus t graph? Well, you might remember that it is the acceleration, but what's the definition of acceleration? Well, average acceleration is change in velocity divided by change in time, right? It's the rate of change of velocity with respect to time. Instantaneous acceleration is a derivative of velocity with respect to time. Anyhow, so the rise is the change in velocity, the run is the change in clock time, so that the slope is change in velocity divided by the change in the clock time, and that is, by the definition, your acceleration. Again, since it's a straight line graph, that acceleration is constant, so that's it. If it was a curved v versus t graph, you would have an average acceleration. Okay, now the area, how do you get the area of a trapezoid? It should be automatic by now. You take the average altitude and you multiply by the width, and you should understand why. You can trim off this little triangle, do this, and you get a rectangle that's equal to the average graph altitude times the width. Or you can slice it like this, put these two together and get the same thing. Okay, well, anyhow, average velocity times the width is, the average velocity is the average of the two velocities. You add them, divide by 2, multiply by delta t to get the area. V bar delta t, that's delta x. So we get acceleration is this. Acceleration is Vf minus Vi over delta t. Well, you just rearrange this a little bit and you get this. This equation is totally equivalent to this one. You can do that rearrangement very easily. Delta x is your V bar delta t, okay, and it's kind of obscured there a little bit. There's a V bar in there. Let's make that a little heavier. And that's what? Vf plus Vi over 2 times delta t, okay? Well, that's this equation, okay? So, whereas with the other derivation, we obtained these two equations, with this derivation, we obtained these two. And then this equation is easily obtained from these two by eliminating what? Vf, okay? Plug Vf in here and simplify, you get this equation. And if you eliminate delta t between these two equations, solve this one for delta t, say, and plug the result in here and simplify it, you get this. So again, you get exactly the same four equations using just basic algebra and geometry and interpretation of graphs, especially interpretation of trapezoidal graphs. So that's much simpler, but that doesn't mean that this isn't really important, because when you have non-uniform acceleration, you often have to use the same sort of tricks that we used in doing this. Okay, so there it is.